In part two of Geologic Time, we will continue exploring relative dating with unconformities, correlation, and index fossils. Layers of rock that have been deposited without interruption are called conformable. A complete set of conformable strata for all of Earth history does not exist. Interrupting the deposition of sediment creates a break in the rock record called an unconformity. Unconformities represent periods when deposition stopped, erosion occurred, and then deposition resumed. Generally, uplift of crust causes deposition to stop, and subsidence causes deposition to resume. There are three types of unconformity that we will look at. An angular unconformity occurs when tilted rocks that have experienced erosion are overlain by flat-lying rocks. A disconformity occurs when sedimentary strata on either side of the unconformity are parallel to one another. And a nonconformity occurs when sedimentary strata overlay metamorphic or igneous rocks. All three types of unconformities can be seen in the Grand Canyon. In this illustration, the unconformities are marked by red wavy lines. Beginning at the bottom of the canyon, you can see the Vishnu schist and the Zoroaster granite. They are metamorphic and igneous rocks, respectively. Where they are in contact with the overlying sedimentary rock of the Unkar group and the Bright Angel shale is a nonconformity. When the Zoroaster granite intruded, it caused the Unkar group to tilt, and this caused erosion. Then the Tapete sandstone and Bright Angel shale were deposited. Where the Tapete sandstone and the Bright Angel shale have contact with the tilted rocks of the Unkar group is an angular unconformity. Lastly, there are two disconformities in the canyon, one between the Muav limestone and the Redwall limestone, and between the Redwall limestone and the Supai group. Angular unconformities like the one pictured here consist of tilted or folded sedimentary rocks overlain by younger, more flat-lying strata. Deformation occurred, then deposition stopped, followed by a return to deposition. A disconformity is a gap in sedimentary rock strata representing a time when erosion occurred versus deposition. They are often difficult to identify because sedimentary strata are parallel. To identify them, we need to find evidence of erosion, such as buried stream channels or inclusions of the rock layer below. Top illustration shows how a disconformity is formed. Beds A and B were deposited. Then, due to uplift and erosion, stream channels were cut into bed B, which left behind some boulders and some gravels. Then some subsidence occurred and a return to deposition. Bed E now encloses the inclusions from bed B, and the stream channels are filled in with sediment from bed E. In the photo below, the white line marks the location of the disconformity between two beds. This is a stream channel that was cut into the lower bed and filled in by the rock sediment of the upper bed. Nonconformities occur when younger sedimentary rocks are deposited on top of older metamorphic or intrusive igneous rocks. Nonconformities imply a period of uplift of deeply buried rocks, then a return to sedimentary deposition. This photo shows the distinct nonconformity between the Pikes Peak granite on the bottom and the Sawatch sandstone on the top. This illustration steps you through a geologic history of a hypothetical region. Read carefully through each step in the history of this region. In the next slide, we will check your knowledge of relative dating principles. Remember that relative dating is very simply putting a sequence of events in order from oldest to youngest or vice versa. Let's work this diagram of a hypothetical geologic region from oldest event to youngest. First, we know that H, G, F, E, and D were deposited in that order by the principle of superposition. Next, those layers were acted upon by tectonic forces and were folded. The next event is Y, a fault cutting across all of the folded layers, followed by A, an igneous intrusion. We know that A is younger than Y because A cuts across Y. The next event is a return to deposition with beds C and B in that order. Correlation involves matching of rocks of similar ages from different regions. Correlation provides a more comprehensive view of the rock record. Stratigraphic correlation is the demonstration of equivalency of stratigraphic units. Lithocorrelation links units of similar rock type and stratigraphic position. Biocorrelation expresses the similarity of fossil content and biostratigraphic position, and chronocorrelation expresses the correspondence in age of chronostratigraphic position. Stratigraphic units must eventually terminate. This termination can be abrupt or gradual. Pinch-outs are lateral changes accompanied by progressive thinning of units to extinction. Intertonguing is a lateral splitting of a lithologic unit into many thin units that pinch out independently. These could indicate a rapid back and forth sea level change. In the next slide, we will look at a demonstration of correlation and examples of pinch-outs and intertonguing. This is a simple example of how geologists take three areas and stratigraphic columns and correlate the deposition. There are four pinchouts here circled in blue, where the sediment supply just simply thins out and disappears. Remember the principle of lateral continuity. The area circled in green in the center is a pinchout with intertonguing at the end. Correlation within limited areas is often accomplished by noting the position of the bed in a sequence of strata and involves matching of rocks of similar ages from different regions. To correlate over large areas, fossils are used for correlation. The principle of fossil succession states that fossils are arranged according to their age. It is very similar to the principle of superposition, where we expect to find older fossils below younger fossils in an undisturbed sequence of rock. To use biocorrelation, though, index fossils are needed. Index fossils are fossils we can use to correlate rocks globally. They must be cosmopolitan. This means widespread. They must have lived for a short period of geologic time. And they must be easily identifiable and abundant. The more unique they are morphologically, the better. This photo is an ammonoid. Several ammonoids are valuable as index fossils in some periods of time. A fossil assemblage is a group of fossils used to determine a rock's age. Fossils can also be used to infer information about past environments. For example, shells of organisms can be used to infer positions of ancient shorelines and seawater temperatures. This illustration shows how we use a fossil assemblage to narrow the age of a rock unit. We have two rock units here that contain fossils, Unit A and Unit B, each of which contain 5 fossils. The scallop shell, the fern leaf, the starfish, and the brachiopod shell are all common between the units, as you can see by the white arrows that denote their ranges in time. These fossils will not help to narrow the ranges of the units by themselves. It is the unique fossils in these assemblages that help limit the ranges when grouped with the more common fossils in the assemblage. In the case of Unit B, it is the trilobite fossil, and in Unit A, it is the dinosaur skull and the tree leaf. This also gives us a time framework for all of the rock, or for the age of all of the rock in between the units with the fossil assemblages. This is the end of Geologic Time Part 2. In Part 3, we will discuss numerical dating of rocks.